Stream brought to you by Portland State University's Learning Center. This is a Physics 232, that's physics for the life sciences class. And today we're going to kind of extend what we talked about last week about magnetism. Last week we talked a lot about magnetic fields and magnetic forces. Today we're going to talk about magnetic fields through current carrying loops. So when you have a loop, how does that magnetic field work? We're going to talk about solenoids. We're going to talk about torques on wires, and we're going to move on to fluids after that and talk about hydrostatic forces and hydraulic forces and pressure. But first, a few bookkeeping things. I'm going to paste a few links in the chat. There is a link to the Learning Center's website, if I can speak correctly, which is www.pdx.edu/learning-center/tutoring. They have a lot of great resources there. There's also a link to the Learning Center's Facebook and Instagram, so definitely check those out. Follow them on Facebook and Instagram if you haven't already. And the next link is an attendance sheet for this live stream. So if you are here, fill out this attendance sheet, and we will try to get that information off to your teacher in case they offer any type of extra credit or anything for being here. Now, going on, we're going to talk, like I said, about magnetism. And we talked a little bit last week about the magnetic field generated by a current carrying wire. If it's a long straight wire, you can find that magnetic field using a version of the right hand rule where you grip. So if this is my wire, you would grip that wire. Your thumb would be in the direction of the current, and your fingers would simulate the direction the magnetic field would radiate around that wire. And that's shown in this diagram here on the screen. We can calculate the magnetic force, where the force is B is going to be equal to I/L cross with B. So that's the current times the length of the wire that you're talking about, crossed in a cross product with the magnetic field that might be generated. That's the force of, let's say, another wire on there. We can simplify that to be I/LB sine of theta, where theta is the angle of between the length of the wire in the direction of the current and the magnetic field. So if those two are perpendicular to each other, sine of theta is going to be at its maximum, which is 1, because sine of 90 degrees is 1, and therefore the force applied on the other current carrying wire would also be at its maximum as well. We can talk about the magnetic field itself generated by this wire would be equal to mu naught, and that's the permittivity of magnetic free space, times I divided by 2 pi r, where r is really just the distance away from that wire that we are. And that could be the distance in any direction perpendicular to it. We can also, so that's a lot of what we talked about last week. This week we're going to talk a little bit about that some more, but we're also going to get into magnetic fields created by current carrying loops. So this is a similar idea. So created by current carrying loops. So hopefully there's when you have current flowing through a loop like it's diagrammed there, you can use a similar type of right hand rule where you grip that wire. Again, your thumb is in direction of the magnetic field, and notice the magnetic field is actually radiating in and then out of that loop, so it kind of radiates around it in all directions. And to calculate the magnetic field at the center of that loop, it's a pretty simplistic equation where we have B of the loop is equal to mu naught I over 2r. So that tells you the magnetic field at the center point right inside of that loop. It won't tell you it over to the left or over to the right or anywhere above and below, but definitely right at the center of that point. You're going to tell you the magnitude and the strength of that magnetic field. And notice by knowing the direction, we can know which way the magnetic field is going into the loop by finding that grip. If it's going into the page or out of the page, or in this case, it's more of an isometric. So, but it's going through the loop from underneath in this case, based on the diagram. So let's try a problem. In this problem, we have a uniform magnetic field which points from the south to the north and has a magnitude of 0.023 Tesla. The straight copper wire, a diameter of 0.808 millimeters, is placed on this field in the east-west direction. So since the magnetic field is going from south to north and the wire is going from east to west, we know that they're going to be perpendicular to each other. So the angle between the direction of current and the magnetic field has to be 90 degrees. So it says find the value of the current flowing through the wire so that it starts floating. This is called magnetic levitation. They give us the density of copper wire there. So why would it float, you might ask? And the reason is we have gravity is kind of pulling it down. So it'll fall, but if there's enough magnetic force generated on it, it will actually kind of float. And for it to float and stay perfectly still, the magnitude of force from the magnet has to be equal and opposite to the magnitude of the weight or gravity pulling it down. So we can say that the force magnetic is equal to, say, mg, the mass times its gravity. And we can find an expression for mass using density. So density is equal to, we usually use this value rho. I'll write this up here, RHO is rho. It looks like a little P. I usually draw it with a little tail so I don't confuse it with pressure or, what's the other ones? There's a few different things you might use it for. Usually when you're talking about gases and other things like that. But so rho is going to be used for density times V, which is the volume in this case, not to be confused with velocity. So we can solve this because this is going to be, rho velocity. Rho is equal to mass divided by velocity. And then therefore we can solve for mass equal to rho V. So the mass of the object is going to equal to the density of the object times its volume. And in this case, we have a long copper wire, so the volume for that is going to be equal to the volume of a cylinder. And we can say the volume of a cylinder is the area of the cylinder times its length. Area can be pi r squared, just the area of a cross-sectional circle of it. So I can say where V is equal to pi r squared, the area times its length, say L. Therefore, we can rewrite the mass equation up here. Mass is equal to the density times pi r squared times length. Now, using this equation we have for the mass, we can substitute that in, change to green, to the equation we had up top here, right? So we can say that the force of magnetism would be equal to the density times pi r squared times length, and we're going to multiply that by gravity. Now, now we can input in this equation that we have for the magnetic force. Magnetic force is equal to ILB sine of theta. In this case, sine of theta is going to be equal to 1 because we're at 90 degrees. There's a 90-degree angle between the magnetic field going straight down, just draw an X, and the current of the wire, the length of the wire. So we can just substitute in ILB is equal to rho pi r squared LG. And I'm actually going to change that to green so I can cancel out in red real quick. And notice that the L's are going to cancel out, so it doesn't matter how long the wire is going through there, because the however long it is, as long as the entire thing is in there, inside the magnetic field, that is, the whole thing should levitate. If some of it hangs out, you're not going to have force on those areas, so those could weight it down. But in this case, we then have this current times the magnetic field is equal to the density times pi r squared times gravity. And we want to find out, ultimately, the value of the current that needs to go through here. Because we can control the current. We can't control the density of the wire, or maybe the length of the wire. And it's hard to control the magnetic fields as much. It's a lot easier to control current going through things. So we want to solve for current. To do that, that's I is equal to rho pi r squared gravity divided by the magnetic field. Now we can substitute in some values that we have for things. We have defined that the density is equal to 8960 kilograms per meters cubed. That's given up here. We have R, the radius of that wire is going to be equal to, it gives us really the diameter. So we're going to have to divide that by 2. That's 0.808 millimeters divided by 2, which if I convert that to meters, be 0.008. Nope. One extra 0.808 meters, all divided by 2, which is equal to 0.000404 meters. So again, that's equal to our radius. Gravity, as long as we're anywhere near the surface of the Earth, is going to be 9.81. That's meters per second squared. And then our magnetic field they give us is 0.024 Tesla. That should be given over here in the problem. So now we have all the pieces we need to solve this. So plugging in these values, we can say that the current is equal to 8960 kilograms per meters cubed times 0.0000404 meters. And we're going to square that because that's our radius. So we want to make sure we're taking our radius squared. I'm going to throw pi in there and then multiply by 9.81 meters per second squared. Divide that whole thing by the magnetic field strength, which is 0.024 Tesla. And we can plug that into our calculator and see what we get. So that's 8960 kilograms per meters cubed. I'm not typing. Why aren't I typing? 8960 kilograms per meter cubed. Multiply by pi times 0.0000404 meters. Outside of the parentheses, I'll square it, making sure I'm squaring the meters and the value itself, times 9.81 meters per second squared. Of course, that's all in the exponent where it shouldn't be. That's better. I'm going to divide that whole thing by our magnetic field. And we get 1.878 amps. So that is the magnitude of the current flowing through the wire. That's the amount of current we would need to flow through the wire to get that wire to levitate in the magnetic field. So we're having that magnetic force counteract the force of gravity going down, and we can actually get some levitation there, which is really cool. If you've ever taken two magnets and kind of put them on top of each other so you can balance it, it's a lot of fun to watch and play with. I like to play with magnets. So in this problem, we have a long straight wire and we have a loop, and they're touching each other just barely. And we want to know what direction the current of I2, this guy down here, in the straight wire, must have to create a field at the center of the loop in the direction opposite to that created by the loop. So here we want to counteract the magnetic field at the center of that loop with the current and the magnetic field generated by the current of I2. So first we need to know in what direction is the current flowing, or is the magnetic field flowing through the loop? Is it going to be going down through the center or up through the center? So we can use that right hand rule where we grip the wire and having our thumb in the direction of current. You can see the current is going kind of up this way based on the arrow there. So if I were to grab that wire, my fingers would have to go down, up, and come out of the page inside of that loop. So that means that this magnetic field is going to be coming out of the page. Remember that circle with a dot in it is a symbol for coming out of the page. So to counteract that, we need to generate a magnetic field of the same magnitude but going into the page from I2. So this one here is, say, B1 for the magnetic field generated by current 1, and somewhere I need to have that same magnetic field, in this case going into the page from B2. And the magnitude at the center point here of both of those two magnetic fields need to be the same. So this has the radius kind of drawn out here. That's going to be the same distance here from the center of that loop down to that wire, because we say that the wire is just barely touching the loop. So that's the direction that needs to happen. Then they ask us, what is the ratio of L1 to L2 that gives you zero field at the center of the loop? Because they're not telling us what the current of L1 is or the current of L2 is, but there's some ratio between those two. If we were to define one, then we could define the other just by knowing this ratio. And to find that out, we need to use the equations for the magnetic fields that we know and love. So starting with, I'm going to start with B2, which is the wire. That's this magnetic field that we've been using, 2 pi r. So mu naught times I2, the current, divided by 2 pi r. B1 would equal mu naught I1 divided by just 2r. The only difference is one has the pi and one doesn't. And since the directions are opposite, we need the magnitudes to be equal. That's really the key part of that. So if the magnitudes are equal for each other, we can basically set those two equal. So mu naught I2 over 2 pi r needs to be equal to mu naught I1 over 2r1, or just r. It's the same radius basically for both of them. So now they have a lot of common factors. Mu naught is in both of them. I can divide by that. We have 2 is in the denominator of both, and r is in the denominator of both. So I can rewrite this equation as I2 over pi is equal to I1 over 1. So we want the ratio. What we're looking for is this ratio, I1 to I2. So to do that, we have to divide each side here by I2. So that's going to say that I1 over I2 is going to be equal to 1 over pi. And that is the ratio of currents that we need to have to make the magnetic fields equal and opposite in that direction. Just 1 over pi. So now let's talk a little bit about the torque on square current carrying wire loop. So this is different than the last wire loops we had, because the other ones were circular loops. This one's kind of square rectangular, which is going to have a width and a length. And the width is kind of going across the top, and we're putting this into a magnetic field. Here's some diagrams here of it, and you see there's a torque, this rotation angle going down at that point there. So it's got this axis that it rotates around, and you can see the wires going this way in the magnetic field on the top and bottom are not going to have much of an effect on it, but these guys here, the vertical wires, if I can draw a cross section of this, it's kind of, so you can see this is kind of the wire here, and you have your magnetic field kind of flowing between it like this. And the forces on the tops and bottom parts of the wire are not going to have any torque associated with them, because at every point along there, the forces are going to cancel each other out. But the vertical lines up and down, those are going to have some torque associated with them, and it's going to be dependent based on the direction of the current going through them. So looking at this first diagram, I'm going to zoom in here. You can see my width is kind of this length all the way across, and we're coming out of the page here and going into the page there for our current, because that current's going to flow in different directions on those two posts on the side. And we're calling this our width, so half of the width is going to be the distance from the end to the center of rotation there. And you can see that the torque is going to be defined. So torque is going to equal the distance of that radius, that should be a 2, times the current LB sine of theta. And again, theta as always is going to be the difference between, in this case, the wire itself, or the radius arm, and the force that's being acted on it, just like we had with torque previously. We can see as it rotates around too, it's going to have different values of torque, because this angle between the arm and the force is going to change. At this point, it's going to be at its maximum, because we have 90-degree angle between those two. So it's going to be pulling down on those two posts the most at that point, and have the most torque there. And when it's 45 degrees, like it was over in this first one, it's still going to have torque. It's just going to be a lot less torque. And then we get to this position where here, where we're going up and then into the page that way, we actually end up with a negative torque. So it's actually going to be pulling back, slowing the axis of rotation at that point, because the torque is now going this direction instead, based on the way the current is. And anytime we have these two here, that means our angle is going to be equal to 0. Our theta is equal to 0, therefore our torque is equal to 0. So one way we could maximize the spin of this is anytime we had from 0, if it was rotating, say, at this point, we could switch the magnetic fields kind of back and forth. So it would go from point A up here, and it would have some torque, and then it would have its maximum torque. They didn't really draw it here, but we could have another depiction where it starts here, goes through, and down here. And that would be similar to part A over here, where it'd still have torque, it would just have less torque. And once we get to part C over here, okay, then we have 0 torque on the system. So it's not slowing it down, but it's not helping it anyways. But it should have some inertia, some momentum, angular momentum spinning, which will let it go past to that point. But once it hits that point, if we flipped the magnetic field, we could actually generate more torque, because suddenly these magnetic fields would be going the opposite direction, and we would actually have continuous torque on the system. Either way, the torque is going to be equal, like I said, to the width, or half the width, times the current L crossed with B. And then that's for 2 parts, because there's 2 segments there. There's this one, and there's another segment here. because there's 2 torques on that system. So the total torque is really going to be twice that. There's a vector there. And we can write the magnitude of that then being equal to WILB sine of theta. And notice W stands for width and L stands for length, so that's the width across the top of this up here, and the length is down here. So that's width and that's length. So to find the total area, we could even define it as the area of this kind of rectangular wire structure. We can say this is area times ILB sine of theta. Oh, I'm sorry, I threw the I in there, or the L in there. I shouldn't have. Oops. Big eraser. Because there's W times L is equal to area. That looks better. And that's for a single wire. So we could make 2 or 3 or 4 wires, and every wire we add to it will increase the torque by another factor. So we could say that that torque is equal to N. The torque of N wires is equal to NAIB sine theta. And the maximum torque is always going to be, as we had here, when your angle is 90 degrees. So that's always going to be the most amount of torque, because that sine of theta term is going to be 1 at that point. So I can say torque max, I should put a little squiggle in my torque, is equal to NAIB, because sine of theta is equal to 1. And that's where N equals the number of wires in there. So let's see if we can apply this concept. I'm going to calculate the magnetic field strength needed on a 240 turn square loop. So that has 240 turns on that loop, which has 16 centimeters per side, to create the maximum torque of 250 Newton meters if the loop is carrying 24 amps. So I'm just underlining all the values that we really need to pay attention to. Using that equation we just looked at, I say NIAB. Remember, since it's asking for the maximum torque, we can assume that we're at 90 degrees and sine of theta is equal to 1. So we can use that maximum torque. And we want to find the magnetic field strength. So I'm going to solve this equation down here for that. So I can say that B is equal to the torque divided by NIA. So that's the magnetic field strength is equal to the maximum torque divided by the number of loops times the current times the area. In that case, we can define these terms where the maximum torque is equal to 250 Newton meters. Make that a better color to see. We can say that the number of turns, N, is equal to 240 turns. It's not really a unit, it's just a number. And the area is going to be equal to, well, it's got 16 centimeters per side. So I can say that's 16 centimeters squared, which is going to be equal to, I'll say 0.16, that's a parenthesis, meters squared, which was 0.0256 meters squared. So that's the area that we have. And the current I is equal to 24 amps. So plugging those in, we have the magnetic field is going to be equal to 250 Newton meters divided by 240 times 24 amps times the area, 0.0256 meters squared. Plugging those into our calculator, we get 250 Newton meters divided by 240 times 24 amps times 0.0256 meters squared equals 1.695 Tesla. 1.695 Tesla. So that is going to be the strength of the magnetic field that's generated to create that torque going around in circles there. Here we're going to talk about a solenoid. A solenoid has a whole lot of loops going around. They're all going to be circular loops as they go through there. So we're stacking up all of these loops in general, and it creates a magnetic field like shown here on the right, where the magnetic field is kind of incredibly strong as it goes through here, but it dissipates kind of going outwards. So over here, there's practically no magnetic field at all, and it gets weaker and weaker over in this area, but it gets really dense right in the middle. So that's going to be the strongest part of the magnetic field in the solenoid. And you can see as the current is flowing through these magnet wire, the direction of current we see here is going into the page across the top and out of the page on the bottom. So the current's kind of coming up and then going down, coming up, going down, coming up, going down, coming up, going down, and so on. And we can, again, use our right-hand rule, kind of sticking our fingers into that solenoid with our thumb going up in the direction of the current to actually see, again, what that magnetic field is going to look like and which direction it's going to be going through the solenoid. If we reverse the current, then we'd have to stick our hand in the other side of it to see the direction of that magnetic field, because the current would then be going the opposite direction. And we can define the magnetic field is then equal to mu naught N I. Notice it's a lowercase n in this case. That lowercase n is used because it equals the number of turns per length. So depending on how close they are together, what gauge of wire you have, and other things, we could actually adjust the magnetic field fairly significantly. You use really thin wire, you can wind it really, really, really fast. You're limited then by how much current you might be able to throw through it, but there's different ways you could do that. This way we thought about the loops per length is really what we're looking at there, and how we can define, that's how we get that strong magnetic field, is each loop adds that magnetic field going into the middle of the solenoid. So looking at a problem for it, we have this solenoid which is wound with 2,400 turns per meter. So I mean, over a meter's distance, it's got 2,400 turns. When the current is 4.4 amps, what is the magnetic field within that solenoid? So using the equation we just talked about, where B is equal to mu naught Ni, where mu naught is equal to 4 pi times 10 to the negative 7. The units for that is Tesla meters per amp. N is going to be equal to 2,400 turns per meter. Because remember, that's turns per length. And our current is equal to 4.4 amps. So just plugging those values in here, we get B is equal to 4 pi times 10 to the negative 7 Tesla meters per amp times 2400 loops per meter times 4.4 amps, which is equal to 4 pi times 10 to the negative 7 value of Tesla's meters per amp multiplied by 2400, and that's turns per meter. Multiply that by 4.4 amps, and we end up with 0.01327 Tesla. 0.01327 Tesla. So that's the strength of the magnetic field that goes inside of that solenoid. And it might seem like a fairly small number, but remember that the magnetic field on Earth, which drives all your compasses and stuff like that, is of the order of magnitude of 10 to the negative 5 Tesla. So this is 10 to the negative 2 Tesla. So this is a much stronger magnetic field than the magnetic field generated by the entire Earth itself. All just using 4.4 amps as well, which is a fairly low current. So let's get into fluids. We're going to talk about density, pressure of and any type of fluids as well in general. There's a few different types of fluids. A fluid can talk about a gas such as the air that we breathe. You can also talk about liquids, water, and other, basically any type of liquid or gas is going to be considered a fluid, and they're going to behave in these fluid-like manners. And some of them are going to be compressible, where you can actually exert a pressure on them and they'll actually compress and get smaller. And some of them, like water, doesn't compress very much. You could put a lot of pressure on it and it's not really going to compress to it all. So those are uncompressible fluids. We already defined density a little bit. We can say density is equal to mass over volume. And the units for that is usually kilograms per meters cubed. And again, this is our value rho that we have there. We also talk about pressure a lot, and pressure is really equal to the force per area, or force per square meter is usually how it's looked at. Or newtons per meter squared is the units for that one. So if you were to apply, if you were standing on 2 feet, right, you'd be exerting a certain force down on the ground. If you lift one of those feet up, as long as you don't fall over, you've just halved or doubled your pressure, because you have the same weight pushing down on the ground, but it's now half as much area that you had on there. So you can increase the pressure just by shrinking the area that you're using it on. You can see that in the equation, because the area is in the denominator. So if you reduce the area, you're going to increase the pressure. If you spread out and you lie flat on the ground, especially you see these people do this on thin ice, they spread their weight out so that all their pressure is not in one particular place. You're increasing your surface area on the ice itself, so the amount of force per square inch or square meter is much smaller. And pressure can be measured in a lot of different types of units. Historically, they've used stuff like millimeters of hydrogen to talk about air pressure and stuff like that. You see that in those, not hydrogen, millimeters of mercury. You see those in the mercury thermometers that they used to use. They stopped using those because they'd break, and then you'd have mercury in your mouth, which is not really a good thing to have. But they also use values of torr and atmospheres and but pascals. Pascal. I should draw. Which is the standard unit for pressure, is the idea. And you could say that I think it's 101, give or take. I think it's 101,000 pascals is approximately equal to 1 atmosphere. So that's approximately the amount of pressure of the gas that's above you when you're anywhere near the surface of the Earth, or near sea level. So if you go to Colorado and you're, a mile up, like they are, the Mile High City, they're going to have a thinner air. They're going to have less pressure and less air above them pushing down on top of them. Versus if you're more at sea level, you're near the coast, you're going to have more air above you. Therefore, you're going to have a higher pressure there. But it's all fairly close to about 1 atmosphere is what we usually say when we're talking about the just basic standard situations. So we're going to go into this problem. This is a fun problem. This diagram, see if I can zoom in so you can see. Here, I'll show you the diagram. I can't show it both, and I'll read it to you. The diagram below shows a human body which is cannulated, where the tubes are inserted into the body's vasculature at 3 heights. So basically at 3 points it's tied into the bloodstream. You have one in the brain, one at their feet, and one at their heart. The blood would rise to the same height in each tube based on the blood pressure at those places. Similar to a column of water at 3 different heights. The tubes can also be filled with a saline solution with a similar density to the blood, which is a safer experiment to perform. For a typical adult, the the height of the head or the heart is 1.5 meters. This is equal to 1.5 meters. The height of the brain is equal to 1.85 meters. And they want to know, using gauge pressure at heart height from the problem, assume the density of the whole of the blood is 1060 kilogram meters cubed, and that the average arterial pressure of the heart of this individual has been measured to be 99 millimeters of mercury. Express your answer to 4 significant digits. So first we want to calculate the gauge pressure at the feet. So seeing my diagram here, the gauge pressure means kind of like, it's not the total pressure. If I were to talk about the gauge pressure on Earth, if you were to have a bicycle tube tire, this is the analogy I always like to use, and you're about to pump it up, you have a flat tire, you fixed it, but there's no air in the tire, really. You would say the pressure is at 0, but really that's the gauge pressure, because the total pressure of that is 1 atmosphere. Because inside of that, even if there's not much air of anything, it's not pushing out or it's not pulling in at any pressure. It's got kind of 1 atmosphere in it. As you start to pump it up, you pump it up to 20 psi, 60 psi, something like that. I forget what bicycle tires go for. But then that pressure that you're adding in there is a gauged pressure, because we are ignoring the idea of atmosphere. This is the pressure on top of the atmospheric pressure that's pushing inwards on it. There's this pressure pushing outwards on it as well. So calculating that pressure at the feet, we can say that that pressure at the feet is going to be equal to the pressure at the heart plus the density times gravity and delta H, where delta H is really going to be the difference between the height of the heart and the height of the feet. So they gave us a few values in that long paragraph that I tried to read. So here we know gravity is 9.81 meters per second squared. We know that delta H is equal to 1.5 meters, because that was the average heart height of a human. We know the density is equal to 1,060 kilograms per meter cubed. That should be meters squared. No, it's cubed. See, I was mixing up pressure and density again. They're both P's. It confuses me. So the pressure at the heart, they said, was equal to 99 millimeters of mercury. And the reason why they used millimeters of mercury historically is they would put mercury in these tubes, and depending on the temperature, the mercury would expand or contract. But it would always be exerting 1 atmosphere up to counteract the atmosphere down. So the atmosphere down would always be pushing down on it the same amount. So as it expanded upwards, it would expand at a constant rate based on the temperature of it. So that's how they use those mercury vials. You could do the same thing with water, but your water tube would end up being like 30 meters tall and about this big around, which is not going to fit inside my mouth to tell me my temperature. But we can convert that. I just like that story, so I like to rant about it. We can convert this millimeters of mercury to pascals by saying that 1 Pascal, this is really just the conversion rate, is equal to 133.32 millimeters of mercury. And that'll convert us to pascals. So let's try that out here. That's 99 times 1 divided by 133.32. Something's wrong. That should be. I had the wrong number of pascals. Oh, it's times 10 to the 4. Okay, yeah. So that's how many pascals it should be. 1.32 times, or say 1. I was trying to 1.32 times 10 to the 4th Pascal. Let me see what one. See if I got that conversion right. I was way off. So that should be the amount of millimeters of mercury there is in a Pascal. That was 0.07501. Was it about double? 0.007571. That's millimeters Hg. Just to have the right units on here. 7501. That's a 0. Okay. And I said that was equal to 1.32 times 10 to the 4th Pascal, roughly speaking. So we can then, and this is the pressure at the heart. So we want to find the pressure at the feet. So the pressure at the feet would equal that pressure. So 1.32 times 10 to the 4th Pascal plus the density, 1060 kilogram per meter cubed, times 9.81 meters per second squared, times our delta H, which is 1.5 meters. All right. So we have our pressure times the density. Times gravity times their delta H, that's 1.5 meters. Pascal. Oh, that should be plus, not a times. Way back here. And it should be 2.87, say 2.880 times 10 to the 4 pascals. 2.880 0 times 10 to the 4 pascals. We can do the same thing now for the pressure at the brain height. And we do that in the same way. Notice up here, I took the pressure at the lower one is equal to the pressure at the higher one plus the density, gravity, and delta H. That's kind of how you find these hydrostatic pressure equations. So doing the same thing here, in this case the brain height is the higher one. So the brain height is going to go here. So I have the pressure at the heart is going to equal the pressure at the brain plus rho times gravity times delta H. In this case, a lot of those same values apply, but now we have delta H is really equal to the difference between the head height and the heart height. So that's going to be 1.85 minus 1.5, which is equal to 0.35. These are in meters. The density is the same, the gravity is the same, and the pressure of the heart will be the same. In fact, yeah, we just solved for that here, even. But we want to solve for the pressure of the brain. So I can rearrange this equation to be P brain is equal to rho gravity delta H minus P heart. No, other way around. P heart first minus that. Because we want to subtract this value from both sides. So now solving for that brain, we can enter the P of the heart. The pressure of the heart, we said, is this value up here. So that's 1.32 times 10 to the 4th pascals minus the density, 1060 kilograms per meter squared cubed. I'm going to multiply that times gravity, 9.81 meters per second squared, and then multiply it by the difference in height, which is 0.35 meters. So I'm going to grab this value up here. That was our pressure of the heart. Subtract from that 1060 kilograms per meters cubed. Multiply that by 9.81 meters per second squared and multiply by 0.35 meters. So equal to 9559.4 pascals, or 9.6 times 10 to the third. Equal to 9.6 times 10 to the third Pascal. And notice this is lower. The pressure at your brain is going to be lower than the pressure at your feet or at your heart because it's higher up. There's less fluid above it. At your heart, there's some fluid above it, so you have a slightly higher pressure. That was this 1.23 times 10 to the 4th. And then at your feet, you have the most pressure because all of the blood is pushing down on your feet in that regard. So now we can solve this problem to produce the pressure at the feet calculated in part A. What height above the floor must the saline solution rise? So that all comes down to that change in pressure. That change in pressure is really just going to be equal to rho gravity delta H. We can solve this for delta H, where delta H is equal to the change in pressure divided by the density times gravity. And in this case, we're going to say that the change in pressure is really just going to be at our feet, because what height was the floor? We have that atmospheric pressure is really the difference between it. So I can say delta P is equal to the pressure at the feet, which is going to be equal to 2.878 times 10 to the fourth Pascal. Remember, rho is equal to 1060 kilograms per meters cubed density, and gravity is equal to 9.81 meters per second squared. Plugging those values in, there it is. We can say delta H is equal to 2.878 times 10 to the fourth pascals. That was our answer from part A. Divide that whole thing by 1060 kilograms per meters squared, and then 9.81 meters per second squared. So that's pascals at the feet level. Divide that whole thing by 1060 kilograms per meters squared times 9.81 meters per second. Should be, my meters should be cubed. I wrote it down in my notes wrong, so everything's wrong. There you go. 2.77 meters. 2.77 meters. That's how that's how high the saline solution would have to be above the floor to give you that same pressure at your feet. And it's that much density of saline solution above it, which that's pretty tall. Taller than I am. So part D asks if the beam arterial pressure, or that should be mean, my spell check screwed me, mean arterial pressure at heart height is 44 milligrams of mercury instead of 95 milligrams of mercury, what complications might arise? So if we're reducing the blood pressure at your heart, that means that there's going to be a lower blood pressure at your head, and there's going to be, it'd still be a lower blood pressure at your feet as well. So looking at the options here, the first one's the blood pressure at the brain height might be very little, causing dizziness or fainting. That's a good possibility because it will definitely be less. So you've cut the blood pressure from the heart down less than half. Second option is the blood pressure at the brain height might be too big, causing ruptures of blood vessels. I don't like that option because we've already said the blood pressure should be lower at the brain height, because if the heart pressure goes down, you see how to solve for the brain height, we had to start with that heart blood pressure. This guy here. So if that's going down, the brain pressure is going to go down as well. So I don't like this one. And then it says no complications would occur. That's possible. I'm not a doctor, but I would definitely bet my money on A as well, because I know low blood pressure is not a good thing, and your brain kind of operates on blood flow and blood pressure. That's all the time we have for this stream. Wish you guys the best of luck. I'm going to paste again into the comments or the chat a attendance sheet. Make sure to fill that out if you want some extra credit from your teacher, assuming your teacher offers it. And have a great week and enjoy physics.